Here is how to prepare for the Oxford PAT. In this video I'm going to go through as many examples and as many parts of the syllabus as possible. Our first step in preparing is the syllabus. You'll be able to find this on the official Oxford website, which I'm going to link into the description. Make sure that you go through every single little point and that you've covered all the theory that could potentially come up. There are several other useful websites. For instance, the website oxfordpat.wordpress.com has some amazing solutions across the years. You will also find some solutions on Physics and Maths Tutor, and I also have a playlist with lots of walkthroughs of problems. Please note that the solutions that you're going to find on the internet, including this video, are not official solutions. I'm not affiliated with the university, so always be aware that there may be a mistake or a more efficient way of approaching a problem. Another thing to note is that for 2024, the PAT will be switching to multiple choice format only. However, Oxford has said that all the previous resources will still be very helpful. After you have covered the theory, I will aim to do every single past paper from the PAT exam that is available on the Oxford website. Focus not so much on the individual solutions, but on the method that you use to get the answer. For instance, you may come across the use of calculus for minimizing a function, finding a stationary point to find a minimum or a maximum applied to physics for the first time. Keep that technique and lots of others that you will discover in your bank of physics tools that you can apply to problems. For additional practice, doing some of the Cambridge entrance exams, for instance the new problems of the ESAT and the past papers on the ENGAA and then the NSAA exam, are excellent practice. Please note that their syllabus though is a tiny bit different and the style of questioning can be also a little bit different, but that is not to worry. If you run out of problems, solving some of the British Physics Olympiads as well is an excellent practice, although keep in mind that the questions are likely to be probably harder than what you expect to find in the PAT entrance exam. Now let's solve some problems. Use the chapters in this video to choose a problem by topic. The drag force on a sphere is related to the radius of the sphere via the following equation, where k is a dimensionless constant, r is the radius. This viscosity coefficient has units of kilograms, m to the power of -1, s to the power of -1. And v has units, and v is just the speed. What we need to do is figure out the coefficients x, y, and z. So these problems are best solved by doing a system of equations. The way to tackle these problems is to write out the units on the left and write out the units on the right. So on the left we have force, which is mass times acceleration, that would be kilograms, m s to the power of -2. K has no units because it's dimensionless, and then we're going to have m to the power of x, meters to the power of x. The units of the viscosity are going to be kilograms to the y, m to the power of -y, s to the power of -y, because they're all raised to the power of y, multiplied by the units of speed, which are meters, so m to the power of z, s to the power of -1, and then this here will be minus z. This here is a z, not a 2. Okay, so now we can equate the units on the left with the units on the right. The next thing we should do in those problems is group all the terms together. So I can go kilograms, m s to the power of -2 will be equal to m to the power of x times m to the power of -y will give me a factor of -y here because of the properties of powers. If we multiply them together, we have to add the individual powers. And then we have m to the power of plus z, like so. Okay, then we have kilograms raised to the power of y. That's the only unit for the kilogram, so we can immediately see that this will be equal to 1. And then this here is going to be multiplied by seconds to the power of -y and then -z. Okay, Now we can equate the powers. On the left we have kilograms to the 1, on the right we have kilograms to the power of y, so we can immediately write that y has got to be 1. Let's move on to this one, so minus y minus z has to be equal to minus 2. We can rearrange for z directly. Minus z will be, what is it, minus 2 plus y minus z will be, because y is just 1, be minus 1, z will just be 1. So we have a 1, and then we also have a 1 for z. We can also figure out what x is going to be, because we know that x minus y plus z, this power here has to be equal to this power. On the left-hand side, we have just m, which is essentially m to the power of 1, and this here is m to the power of 1. Okay, so we know that x minus y, they're both equal to 1, so minus 1 plus 1 is just equal to 1. Okay, we can just see that those are just removed, and then x is just equal to 1. So a lot of the wave questions in the pad are pretty similar to the theory that is based on waves as taught in A level. However, there's one particular equation that I've seen come up, and this is this one, which is definitely not taught in A level. And that is the solution of a traveling wave. So I'm going to show you the general solution. What we need to remember is that y over x of t is equal to a sine of kx minus omega t. This is just a general equation for a traveling wave. You can also use cos, by the way, so yx of t is a cosine of x of t minus omega t. So what we need to remember is that a is the amplitude, k is a quantity which is known as the wave number, and k is simply defined as 2 pi divided by the wavelength, and omega is just the angular frequency. So there's several equations that are very useful for omega. Omega is 2 pi over the time period, but it also is 2 pi f, like that. Okay, now with that in mind, these problems become so much easier. So for instance, we're just going to focus on the first two parts of the problem to illustrate this. What is the period of the ship's vertical oscillations? Well, in order to figure out the period, what we can do is just expand out this equation. So let me just rewrite this over here. Let's switch back to black. Yx of t is equal to a sine, and then we have 2 pi over lambda multiplied by x. I'm just literally expanding brackets. Take away 2 pi v divided by lambda, like that, multiplied by t. Okay, so what we can see is that what we have here, 2 pi v over lambda, this here is our angular frequency, which is also equal to 2 pi over t. So we can essentially set those equal to one another. We can say that 2 pi v divided by lambda is equal to omega, which is equal to 2 pi divided by the time period. Okay, so because of that, I'm just kind of focusing on the furthest left and furthest right. The 2 pi's are going to cancel, and we know that v over lambda is 1 over the time period, meaning the time period is just going to be lambda over v, and this makes sense in terms of units. It's always useful for the part to do a sanity check at the end. So for instance, we have meters over meters per second, which just gives us units of seconds, like that. Okay, part B, what is the total vertical distance the ship moves during a time interval equal to the one time period? In one complete time period, then the ship is going to go up to the amplitude, but then it's going to go down to the negative amplitude. So the total vertical distance should just be equal to 2a. Okay, let's move on to some electricity questions. We've got a particle with a charge q, an initial speed v, stopped by a potential difference v, and a time d and t. What is its initial momentum? Okay, so these problems are typically done by using the definition of work done. So we can say that work done is equal to the voltage multiplied by the charge. So the work done itself, though, if the force is parallel to the direction of motion, which in this case we assume it is, this here will just be equal to force times distance will be equal to V times Q. Okay, now our force, though, is equal to the rate of change of momentum, delta P over delta T. So because it is fully stopped, our change of momentum will be equal to the final momentum. So all we need to do is find our delta P, which will be equal to F multiplied by delta T. So what would that be equal to? Our force is equal to VQ over D. So this means that our change of momentum will be equal to F delta T, which means that our change of momentum will be equal to the force, which was VQ divided by D multiplied by delta T. Okay, so looking at the answers, this corresponds to answer A. We've only taken the delta T, which is equivalent to a time period T. Okay, next one, we've got a network of capacitors shown. All capacitors in the network have the same capacitance. Assume that the capacitance combine as follows. So let me just write this down for your notes here, but if two capacitors are in parallel, then C total will be equal to C1 plus C2. If the capacitors are in series, then we have 1 over C total is equal to 1 over C1 plus 1 over C2. The way I typically write this is that C total is 1 over C1 plus 1 over C2 raised to the power of minus 1. So they add up the same way as resistors, but opposite. Okay, so how are we going to tackle this problem? So first of all, we have two in series, and if we were to add these up, then those two are just going to halve. So those ones here will be equivalent to half C. So this is those two combined. Okay, now the other thing that we can simplify is that those two together are going to be equal to 2C because they are just in parallel. Okay, and then one of the trickiest bits is that this diagram can be a little bit confusing, but all three of those are actually in parallel. I mean, it's just the length of the wire which is different. This circuit is completely equivalent to this circuit across here, and because all three of them are in parallel, then these are equivalent to a circuit of 3C. So in fact, let's first of all figure out the total capacitance for the middle branch. So what would that be equal to? You have C and 2C in series. So C total for this branch will be equal to 1 over C plus 1 over 2C raised to the power of minus 1, which is just going to give me 2 over 3C. Okay. So let me just kind of write this a little bit clearly. The combined capacitance for the upper branch is half a C. The combined capacitance for the middle branch will be 2/3 C, and the combined capacitance for the lowest branch is just going to be 3C. So my final step in this will just be to do half a C plus 2/3 C plus 3C. Okay, so let's put all of these into a common denominator. So what is that going to give me? 3c over 6 plus 4c over 6 plus 18 over 6 multiplied by c. Multiply them all together, we're going to get 25 over 6c. Okay, next one, consider the above circuit. The filament lamp A consumes electrical power 100 watts when it's alone connected to the voltage of 100 volts. Filament B consumes a power of 20 watts when it's alone connected to a voltage of 100 volts. When the switch is closed, which lamp is brighter? And we have a hint over here. We want to figure out the ratio of the level of brightness of the two lamps, assuming their resistances are constant. Assume further the brightness of a lamp is proportional to the power that it consumes. Okay, so a good starting point is that we can just apply the equation that P is equal to V squared divided by R. So for the resistance of A, which is going to be V squared divided by P, what we are going to get is the following. So I'm just write this: V squared divided by PA. What is that going to be? If the voltage is 100 squared, divide that by 100. Well, this here will just give me 100 ohms. Okay, so far so good. Let's figure out the resistance of B. So RB will be exactly the same, 100 squared over the power of B, which is 20. That will be 1000 over 20, which is 500. That'll be 100 squared over 20, excuse me, which is 500, like that. Okay, so then we can just compare the actual two powers. The current for them will be the same. So if the current is the same, we can just do PA over PB, for instance. So let's also use that the power is also equal to I squared multiplied by the resistance. So let's do one over the other. So I'm going to do PB over PA, like that. So PB will be equal to I squared multiplied by the resistance of B over I squared times the resistance of A. I'll be able to figure out the factor between them, which is a technique which comes up quite often in the PAT actually. Okay, but because they're in series, we can just get rid of the current. Okay, so far so good, because it's just going to be constant. So what would that be? RB over RA, that's just 500 over 100, which is just going to be 5. So the judging by the assumption, we can say that lamp B will be 5 times brighter. Okay, B, how would your answer change if the lamps were in parallel rather than in series? Okay, so the answer will change quite dramatically. We can probably do this over here on the side. So for B, the critical bit is that whenever we have things in parallel, the voltage will be the same between them. So we can probably use the ratio, given that we know their resistances, but I'm just going to write that in parallel, V is constant. And this is what we'll be able to cancel out from our equation. So once again, I'm going to do PB over PA. So if that's the case, PB will be equal to V squared divided by RB, like that, and divide that by V squared over RA. Okay, so this here, the voltage will cancel out because it's just going to be constant if they are in parallel. So we're going to get 1 over 500 over 1 over 100. So this here will give me 100 over 500, which is just going to be 1 over 5. So now we've got a completely different, well, essentially we have the opposite result. We have the fact that the bulb, the filament lamp A, will be 5 times brighter. This is really interesting. One that might be worth exploring in the lab as well. But yeah, fun little practical. Here's a tricky question about resistors. So consider the resistors array below. All resistors are identical. Calculate the total resistance between A and B. Okay, well, let's say that they're all given by the resistance of R. So this one here is going to be R. We have R and R here, so that's going to give me 2R. That together they're in parallel. So I can just say that for A, tell you what, let's just write A over here. I can say that R total will be 1 over R, that's the first branch, plus 1 over 2R, which is just this branch over here. Let's see if we can figure out what the third branch is. We have an R here and an R here, so that's combined of half an R. And then I have another R here. I can completely ignore these lines, by the way, because no current is going to flow through them unless we had something connected with them. They serve no other purpose. So half an R plus R is going to give me 1.5 R, which is just 3/2 R, like that, all of it raised to the power of -1. So half an R plus R is going to give me, for the lowest branch, 3 over 2R. So 1 over that will be 2 over 3R, like that. Raise all of it to the power of -1. Okay, so if we were to work these out, we're going to get around 6 over 13R, like that. Okay, part B, if the potential difference V is applied between A and B, calculate the power dissipated in the resistor between B and D. So how much power is going to be dissipated through here? Okay, so a good way to, let's get rid of the other stuff so we can just focus on the diagram. A good way to think about this is that there's 3 branches and they're in parallel and they're all going to have the same potential difference. So the potential difference is going to be V across here, it's going to be V across here, and it will also be V across there. So the potential difference VBD will be given by the current that flows through this branch, we can call that BD, multiplied by the resistance R. The question is, how much of a potential difference is actually going to flow? Well, we know that the potential difference across the entire branch, so I'm going to say across the branch, will be given by the current multiplied by the total resistance of the branch, like that. But we've already figured out that the resistance of the branch is 2/3 R, isn't it? Oh, sorry, 3 over 2R. Right, 3 over 2R. If I add those and that. So what I'm going to get is that V is equal to IBD multiplied by 3 over 2R, meaning that IBD will be given by V multiplied by 2 divided by 3R. So that will be 2V over 3R. Now I can take this and I can sub this into here, and what I'm going to get is that VBD will be given by current was 2V over 3R, multiply that by R, and I'm going to get 2/3 V. So the potential difference across there will be 2/3 of the actual voltage V. So C has a really interesting solution that can help us answer similar types of questions. So one of the first things that I need to do is just tidy up the diagram. So I'm going to make a rule here, and I'm going to say that if 2 points on a diagram have the same current and potential difference, then they're essentially the same point. So we can tidy these up. So we can see that A and D are different, B and D are different. However, C and B are essentially the same, aren't they? So assuming that this is the junction, straight after B, the current will split into two, but at B, the current will be exactly the same. So because of that, we can redraw this diagram essentially kind of like this. So this here is CB like that. Now, if this here is R, then what are we going to have? We're going to have 2R across here. And then we're also going to have another one, which this one here is half an R, so we can write 0.5 R. And then we have, well, this here is A, and then this point here is D. Okay, and then we have another resistor here, which is R like that. Cool. So far, so good. What we need to do is calculate the total resistance between C and D. So we want to, if we were to apply a potential difference between those 2 points across here. Ooh, what's happened? Let me try that again. And across here, we're going to have some current, we're going to have some potential difference. If we were to divide those two numbers, we're going to get the total resistance. This is what the question is physically asking. So it's probably a better idea to redraw the circuit yet again, but we are just going to go kind of this way. So I'm going to redraw the circuit here. Let's start off with D. Then from D, we're going to go to the for these two essentially, which have a combined resistance of half an R or 0.5 R. Then there's a junction, isn't there? Like that. And we are going to go into this circuit. So that's R. And underneath we have 2R like that. And then we have yet another junction like that. And this here we point C. And then we have this part of the circuit, which is just this one here, like that. Okay, and then what we want to figure out is essentially this, between C and D. How much of a resistance there will be between those 2 points? Well, the way we're going to tackle these is the following. So first, let's just simplify this upper branch across here. Then we're going to worry about the resistance R here. So just for the highlighted bits, the total resistance will be given by R over 2 plus R plus to 1 over r plus 1 over 2r. Let me just write this down so I'll show you where it comes from. 1 over r plus 1 over 2r raised to a power of -1. Well, this here will just give me r over 2 plus 2/3 r. We've already calculated that. Okay, let's put these underneath a common denominator. So we're going to get 3r over 6 plus 4 over 6 multiplied by r, which means that this here will be 7 over 6r. Now, this is only for the highlighted bits, so it does not include this resistor across here. So for the whole thing, now let's imagine that in the real world there's no gap between those 2 points. So we can imagine completing the circuit this way, which it is actually on the diagram. The way to tackle these is because we've already found the entire bit above, we can represent this by a resistor of value 7 over 6r, which is in parallel with another resistor of resistance r, like that. And now this is a pretty simple circuit. So let's see if we can calculate the total r for this combination, for the entire circuit between those 2 points. So what is that going to be? It's going to be 1 over r plus 1 over 7 over 6, which is going to be 6 over 7r raised to a power of -1, plus 6 over 7r raised to the power of -1. Okay, let's put these underneath a common denominator. So we're going to get 7 over 7r plus 6 over 7r raised to a power of -1. 7 plus 6 is 13. So this here is, once we flip that over, 7r over 13. And I think that's the correct answer. Okay, next one. In the resistor network shown below, each rectangle represents a resistor with fixed resistance 12 ohms. In each circle, a water heater with resistance 6. So all of these are essentially resistors. So tell you what, let's just write these down. So this one here is 12 ohms. Each water heater contains 1 kilogram of water, initially at 20 degrees, and you may assume that all power dissipated by the water heats the water. A voltage of 84 volt is applied as indicated in the figure. How long does it take for each individual water heater to raise the water temperature to 27 degrees? Okay, so one of the things to realize with those diagrams across here, I'm just going to draw this here, but this is pretty much equivalent to the positive and negative terminal of a battery, like that. So if that's the case, it will be a lot easier to think about our circuit. So think about this as the beginning of the circuit, and this here is the end. In a way, you can think of it as a complete loop. The only difference is that they've not represented the complete loop with, with a loop, but with a straight line. Okay, so in our head, this will make the problem a little bit easier. So in order to work out how long does it take for the water to raise the temperature, we're going to need to work out the power. My plan of action is to use E is equal to mc delta theta. Remember that energy is power times time, which is equal to mc delta theta. Just a little note that this equation is no longer on the pad specification. Sometimes things like that can appear, especially if the equation is actually given, but this is an older style question. I'm not 100% sure if this was on the specification when the question appeared, but yeah, hopefully you guys have studied this in A-level already. Okay. So once we figure out our power, we're essentially in business. So the way we could figure out the power, because we have the resistance, would be to use that power is equal to V squared divided by R. How are we going to figure out the voltage across them? Well, let's use just Kirchoff's second law. So I'm going to go through one complete loop. So if I was to start at the positive, if I was to go from here to here, then I'm essentially doing one complete loop because I'm starting from the positive terminal and then I'm going all the way around back to the negative terminal. This here counts as a complete loop. So essentially this is equivalent to a circuit with two identical resistors, like that. And if the two resistors are identical, we have 84 volts and then we have R and R, the voltage will be perfectly split. So we can say that the voltage across B has to be equal to the voltage across C, which has to be equal to 42 volts. And then this means that we can work out the power, which is going to be across every one of them, which is going to be 42 squared divided by 6. That gives me 294 watts. Okay, I've got the power. I can just substitute that into here for the first case. So we're looking for the time, aren't we? Which is going to be MC delta theta divided by the power. I think I've got pretty much all of the quantities. It's 1 kilogram multiplied by 4,200. We're given the specific heat capacity. Okay, change of temperature. We're going from 20 to 27, so that's just going to be 7 degrees. Divide that by 294. Okay, plugging in all those numbers, so we're going to get around 100 seconds, and that's for B and C. Now, here's something really, really interesting. What will the voltage across A actually be? Well, I'm going to take two more loops. From the positive terminal, I can also go this way to the negative terminal, and this is actually another complete loop. So this would mean that between the positive and then the negative terminal, if I was to go around here, then I'm going to go through yet another two equal resistors, which means that, let me just write those in blue maybe, but those two will be on 42 volts and this one here will be on 42 volts. But the ones below were 42 volts and then 42 volts here. So how much voltage will there be through A? Well, let's take one final third loop across the actual circuit. So the total, Kirchoff's second law says that the sum of the EMFs has to equal the sum of the PDs. So the EMF is 84 volts, which has to equal to, okay, let's take the final loop. We're gonna go this way. Okay, we have 42 for the first one. We don't know this one. I'm gonna take, so I'm gonna call that VA. Now I'm gonna go this way, so plus another 42 here. So we can clearly see that VA has to be 0 across this green loop across here. So if VA is 0, then, well, the water doesn't heat up. So we can just say the water in A does not heat up. Once we do a few of these, they tend to feel a lot easier. There are several formulas that we need to be aware of for circular motion that appear quite often on the pad. If we have an object of mass m that is moving in a circle, then it's going to experience a centripetal acceleration, which will be always towards the center of rotation, and this here will be given by its linear speed divided by the radius squared. Because of that, we can also say that mass times acceleration will be mv squared divided by r, and this here is the net centripetal force. When something is moving in a circle, the resultant force is always towards the center of rotation. We can also define the angular velocity omega as the amount of angle that this thing travels, let's say it travels an angle of delta theta in some time t. So the rate of change of angular displacement is our angular velocity. If the angle is 1 full revolution, this here will be 2 pi, which will correspond to 1 time period t. We can also write this as 2 pi times 1 over t, which is just equal to 2 pi f. Another equation which is often very useful is that our linear speed, so this here is the angular speed, is 2 pi multiplied by the radius divided by the time period. This is just the distance divided by the time, where 2 pi r is the circumference. Okay, so 2 pi r divided by t, but hang on a minute, 2 pi is just 2 pi over t is just that. So another way we can write this is that v is equal to omega r. And we can apply these to some problems. So here is a circular motion problem. We've got a child of mass m stands on a platform which rotates freely at an angular speed omega. The child's center of mass is initially at a radius r0 from the axis as shown. The child now slowly pulls itself closer to the center of the platform. State the minimal force Fr needed to pull the child closer to the center as a function of the radius. Okay, so the way I think about this is that there's a certain amount of minimal force required for the child to just be rotating around. That minimal force is given by mv squared over r. So in order to make an object move towards the center, the force needs to be greater than that value. Just to make it absolutely clear, the force needs to be greater than that. So we want this though as a function of the radius. And I think this is what can make the question a little bit trickier. The speed, the velocity depends on the radius because remember v is equal to omega r. So this means that f has to be greater than m omega squared r squared divided by r. It has to be greater than omega squared r. So the minimum force really is, or the threshold speed is m squared r. Okay, part B, what do we need to do? Find a mathematical expression for the work done by the child when it has reached the center of the platform. Okay, so we can take the work done along the path to be f of s ds, where f is a force in the direction of motion. So I'm going to say that the work done is equal to the integral of the force dr. Now, if we're starting from r0 and we end up at the center, we are essentially ending up at 0. So these will be the two boundaries of my integral. Okay, so this here will be integral from r0 to 0 of m omega squared multiplied by r dr, and this here will just be given by m the integral of omega squared r dr from r0 to 0. Typically, I would take omega outside of the integral sign. However, technically, we're actually changing what is known as the moment of inertia as the child is going. So there might be an effect on the angular velocity, but let's see the rest of the question for that. Into which form of energy is the child's work converted, and what will qualitatively happen to the angular speed as the child approaches the center? Okay, so it is converted to kinetic energy, and we are expecting the kinetic energy to increase, and hence hence omega, the angular speed, to increase, similar to the way that let's say a ballerina or an ice skater will speed up when they pull their hands closer to a center. So we're expecting omega should increase, or let's say will increase, like that. Part D, the angular momentum of the system of the child on the platform is conserved. It is defined to be, and we've got a brand new expression here. Angular momentum is given by this new quantity for us known as the moment of inertia multiplied by omega, where I is given by this expression mr squared plus IP, where IP is the constant moment of inertia of the platform. Okay, so it's a constant. Find an expression for the angular speed as a function of the radius. Well, as far as I can tell, the angular momentum J is going to be given by brackets mr squared plus IP multiplied by omega. We can directly rearrange for omega, and this here will be J over mr squared plus IP. And now we've got omega as a function of the actual radius. Okay, so far so good. Now part E, we need to find the total work done by the child when it has reached r is equal to 0. So in the previous part we essentially did an integral. We said that the work done will be equal to the integral of the force between 0 and r naught, and then we've got omega squared multiplied by r dr. Now it's time to evaluate this integral, and notice that they've given us a hint which is going to make the integration a lot easier, hopefully. So let's see what we get. We're going to get m, the integral of omega squared. So this here will be j squared over mr squared plus IP squared, such as that, multiplied by r dr. Let's take some constants outside of the integration sign. So we're going to get mj squared, the integral. This integral, by the way, is between 0 and r naught. Okay, 0 r naught. What do we have inside? R over mr squared plus IP squared, such as this. Now let's compare this to the integral that we're given, and notice that the integral is of the order of x over x squared, and here we have m over mr squared. So what I'm going to do is essentially divide both sides of this fraction by a factor of m squared. So this should work. What we're going to get is j squared divided by m squared. That's just going to give me j over m, and then the integral of 0 r naught as the boundaries. We'll just have a factor of r. And then inside of the brackets we're going to have r squared plus IP over m, because this thing is squared like that, dr. Okay, I think that's right. So now we have the form of the integral of the exact form as the one that we're actually given. And we can integrate this. This here will be equal to -1, so let's say minus j squared over m, and then we are going to have a factor of 1 over 2 times a, which is I subscript p divided by m, plus x, which was r squared, such as this. And this thing here is evaluated between 0 and r naught. Okay, I'm going to evaluate this over here. And this here will be equal to minus j squared over m. And then what do we have? We have 1 over 2 IP over m. So here will be IPM. That will end up cancelling most likely. Minus. Then what we're going to get is a factor of 1 over 2 times IP over m plus r naught squared, such as this. Okay, so then what we can do is essentially multiply the entire fraction by a factor of m. So let's just do that in red. This here will be times by m. This here will be times by m, which will end up cancelling. And then we're also going to get a factor of m multiplying the r naught. So let me just rewrite this properly. This will be minus j squared over m. The m's are going to cancel here, so what do we get? 1 over 2 times ip, and then minus 1 over 2 times ip plus m r naught squared, like that. I'm going to take the factor of 2 out as well, just to tidy the expression up a little bit. So this thing here will then equal to minus j squared. Now all those factors of m here will have cancelled, and what we're left with is, let's take the factor of 2 out as well. So there'll be 1 over ip, take away 1 over ip plus r naught squared, such as this. Okay, now notice something really interesting. Omega was j over mr plus ip. Oh, we've missed a factor of m here, so let me just correct that. Ip plus mr naught squared. So if I was to split this j into 2, j times j, this thing here is actually going to equal to minus j over 2. The angular speed evaluated at r is equal to 0 without this term. So omega at r is equal to 0. Take away omega at r is equal to r naught. I think that's right. Cool. So this here is actually a really fun and interesting result. Another topic that appears very often on the PAT is the gravitational fields. Okay, so one of the main formulas that is being used is Newton's universal law of gravitational attraction. So if I have two masses, let's call one of them m, another one, let's say of mass lowercase m, they're going to experience a gravitational force of attraction which will be equal and opposite. Let's say that the distance between their center of masses is equal to r, then the gravitational force will be equal to a constant, which is tiny, 6.67 times 10 to the power minus 11, multiplied by the product of the two masses, then divided by the square of the distances between them. And this here is the gravitational force. We can also define the gravitational acceleration simply by considering the acceleration of one of those masses. Let's consider this one. We can say that if this is the only force acting on it, m times a will be given by gmm divided by r squared. This is just the magnitude of this force, meaning that the acceleration will be given by gm over r squared. Because this is an acceleration due to gravitational forces, it's often given a different symbol, and you would have seen that in A level as g, which is just gm over r squared in magnitude. Let's do some gravitation questions. So the acceleration g due to gravity on a spherical planet in any universe is given by this equation. So in a different universe, the gravitational constant is g prime and has twice the value. Find the ratio g planet over g Earth for a planet in a different universe which has half the radius and twice the actual density. Okay, so one of the things that I see immediately is that we have mentioned the word density. And if we have mentioned density, it's really useful to actually express the equation into this form. I'm going to say that G will be equal to Gm over R squared. But remember, mass is density times volume. So I'm going to say that this is equal to G multiplied by the density divided by the radius squared. Now, what is the volume? Remember, the planets are just spherical, so the volume is just going to be 4/3 pi r squared. So we can say that this here will be equal to G multiplied by rho, and then 4/3 pi r cubed, and we also have a factor of r squared down here. Okay, so this means that the gravitational acceleration G, after we cancel some of these expressions, will just be given by the gravitational constant multiplied by the density of the planet, and then we've got a factor of 4/3 pi multiplied by r. Okay, so anytime we have a ratio, something will cancel out. You can do this immediately to save time thinking about ratios, but in the video I prefer to show you the more rigorous approach. So the ratio of the planet divided by the ratio of divided by G on Earth. So G of planet over G on Earth. So the gravitational constant is twice its value. So at the top, rather than G, I'm going to write 2G. And then the density is twice the density. So I'm going to write 2 times the density. And then the radius is halved, but I'm just going to have a factor of 4/3 pi before that. And then I'm going to get a factor of r over 2. Okay. At the bottom, I'm just going to have G rho 4/3 pi multiplied by r. And now we can do one of my favorite things, and that will be to be cancelling things out of an equation. So the factor of G can go, the density can go, the 4/3 can go, the pi can go, the r can go. And what we're going to be left with is essentially, well, this 2 and that 2 will cancel out. So the answer should just be equal to 2. So let's see which answer would that be. Correct answer is A. Okay, cool. Moving on. For the next one, it's going to be using the same type of equation most likely. So the gravity on the moon satisfies the equation that G of moon is equal to the 6th of the gravity of the gravitational acceleration on Earth. A ball is dropped on Earth from a height h and takes a time t to reach the ground. So let's just do a little drawing. We've got a ball. We drop it from a height h. From what height it should be dropped on the moon so that it takes the same time to reach the surface? Okay, well, what is the relationship between height and time in this equation? So we know that height is equal to ut plus a half at squared. Let's call it gt squared. There's no initial velocity because this thing is just dropped, so we can get rid of this. So we can say that the height is equal to a half gt squared. We can see that there is a direct proportionality between the height h and the gravitational acceleration g. So if g drops by a 6th, then the height must also drop by a 6th if we were to keep the time constant. So if this thing goes down by a factor of 6, then this thing here should also do the same, keeping the factor of t squared and hence t a constant. This means that the correct answer has got to be B. Okay, next one. If the gravitational field strength of the Earth's surface is 10 newtons per kilogram and a distance r which is greater than the radius of the Earth, the field strength is 2 newtons per kilogram, what is the radius of the Earth in terms of r? I tend to do these problems just by thinking about proportionality. So we know that the gravitational acceleration g of Earth is equal to gm over re squared. So what I'm going to do is I'm going to express the factor of gm in terms of these. So gm will be equal to ge multiplied by re squared. Gm will just be equal to 10 multiplied by re squared, like this. Okay, so now we got a factor of gm. So what we're gonna get now is gr. The same equation also applies for gr, so that's going to be gm over r squared, its magnitude at least. This means that we can say that 2, because we're given that at a distance r, the gravitational acceleration is 2, will be gm over r squared. But hang on a minute, we already have this relationship for g, so we can just plug this into here. Right, what are we going to get? We're going to get that 2 is equal to, around the gm, I'm going to write 10 multiplied by re squared, and then divide that by r squared, like that. Now we can rearrange this for re squared, which is just going to give me 2 over 10, which is 1 over 5, and then we get a factor of r squared like this. So let's take the square root of everything, and I'm going to say that re will be given by the square root of 1 over 5 multiplied by r, which is just going to be r over root 5. So hopefully that corresponds to an answer. Yep, correct answer is D. Next one, 2 moons occupy circular orbits around the planet. The smaller moon has a mass of this much and such orbital radius, and then the larger moon, so here is our planet, and then we've got a couple of moons orbiting around it. Okay, if the gravitational force exerted by the planet on the smaller moon is 10 to the power 14 newtons, what force does the planet exert on the larger moon? So this is similar to the previous question. I'm going to call the smaller moon M, and then the larger moon, let's call it M subscript L. Okay, so let's let's write down some equations. For the smaller moon, the force exerted will just be the gravitational force, which is just given by gm, where capital M will be the mass of the planet, multiplied by the mass of the smaller moon, and then divided by its orbital distance squared. This is just Newton's law of universal gravitational attraction. So for the larger moon, the equation will be pretty similar. So FL will be given by GM and then multiplied by M subscript L. This is a subscript, not multiplied by length, divided by R, and then let's give the R a subscript as well. So R subscript L squared is just the orbital distance of the larger moon. So in order to find this force, we're going to need the mass of the planet, or in other words, this factor of GM. So I'm just going to say over here that GM will be given by F multiplied by R squared divided by M. Now quickly I'll check that we can actually just calculate that. We know the force, that's just here. We know the orbital radius, that's just here, and we know the smaller mass here, so we're pretty much in business. We can directly just substitute those numbers into this equation, and we should be fine. Okay, so tell you what, rather than GM, I'm just gonna write F times R squared multiplied by M subscript L, and then we're going to be dividing that by a factor of R subscript L squared, and then we also have a factor of M from the previous equation. Okay, let's plug in some numbers. So we're going to get 10 to the power 14 multiplied by 2.3 multiplied by 10 to the power 4 squared, multiplied by the mass, which is the mass of the larger moon, which is 1.1 times 10 to the power of 16. And then we are going to be dividing that by, let's see what we have, 1.5 times 10 to the power of 15, that's just the mass. And then we have the distance squared, which is, let's see, 9.4 multiplied by 10 to the power of 3. Do not forget the square, like so. Okay, this here is just going to give me 4.4 times 10 to the power of 15 newtons, meaning that the correct answer is E. Okay, next one, we've got a certain binary star systems. Two stars with identical mass have equal and opposite velocities. So I'm gonna have one star being across here and then another one there, and they have the same velocity, which is v2, going in opposite direction. Okay, so then in another system we have three stars with the same mass as before, and it is observed that all three stars are equally spaced around a circular orbit with the same radius r before. Okay, this is really interesting. I think they're going to form an equilateral triangle. So we're going to have one over here, one, let's say, over here. This one here is M, this one here is M, and then this one here is M. So what this question is asking is, what is the speed v3 of these stars in terms of v2? Okay, well, let's figure out the speed of... let's first of all find an expression for the speed v2. So I'm just going to say that mv squared divided by the radius, and that's v2 squared, is equal to gmm divided by, okay, well, the distance between them will now be given by 2r squared. So we can just say that this is 2r and then squared. Okay, let's do a bit of cancelling out. The factor of m is going to go, and one of these factors of r is going to go. So what we are going to be left with is an expression for v2, which is that v2 will be given by the square root of, let's see, the factor of g remains, multiplied by the mass, lowercase m, let's be careful here, gm over 4 times r. Okay, the way to think about this is that we're going to need to know the distance between them to work out the gravitational force and hence work out how fast they're actually traveling. So let's start off by just writing some of the things that we definitely know. Because they're equally spaced, this here will be an equilateral triangle. So this here will be 60 degrees, this one here will be 60 degrees, this one here will be 60 degrees. The distances between them are equal, but the radius of the orbit remains the same. Okay, so let's draw the radius and be quite careful drawing it. So the center of the circle will be somewhere there, and then this distance here will be r that I've just drawn, and then this distance here will also be r, and then this distance here will also be equal to r. Okay, now what about in terms of the angles? Now by symmetry, if this line here is going to go right in the middle and this entire thing is 60 degrees, so I'm pretty sure that this one here will be 30 degrees, and then this would mean that this one here will also be 30 degrees. This one here is R, this one here is R. So if I was to drop the height of this triangle, we've got a 60, 90, 30 degree triangle. So if this angle here from here to here is 30 degrees, then we can find an expression for this distance here, which is just going to be, let's just say that cosine of 30 degrees, that's the adjacent, is going to be this distance, let's call it x, over the hypotenuse, which is just r, so x will just be r cosine of 30 degrees. Now there's two of them, because this one here is x and this one here is x, so the distance between the 2 points, you can just say distance will actually be given by 2r cosine of 30 degrees. And now we are actually in business. We can calculate the actual new speed. So what I'm going to do is I'm just focus on one of these masses, m. So I'm going to say that mv3 squared divided by its radius of rotation. Now its radius of rotation will just be r, because the radius is unchanged in this particular orbit, will be given by the net force which acts on it. Now here's where it gets a tiny bit more complicated. Well, imagine that this mass is here. What forces is it going to experience? Well, it's going to be attracted by this force, by this mass across here. So this means that there will be a force F acting here, F acting along here. All these angles here, by the way, are 60 degrees. So notice something. The horizontal components are just going to cancel out. It's always useful to use symmetry in this case. And if the horizontal components cancel out, then the net force will be given by twice the vertical component, which if this angle here is 60 degrees, then the vertical component will be F sine 60. This one here will also be F sine 60. So this means that the net force which acts on it will just be given by F sine of 60 multiplied by 2. Okay, now what will that force actually be? Well, the force F, I am just going to write this over here, will just be given by GMM divided by the distance R3 squared. So what would that give me? 2r cosine of 30 degrees. All of this is squared. Okay, now let's plug this into here for F and let's see what we're going to get. Sine of 60 multiplied by 2, and then we're going to be dividing that by 2r cos of 30 degrees squared, like that. So this here is going to give me GMM sine of 60 multiplied by 2, divide that by 4r squared cosine squared of 30 degrees. Okay, we're ready to do some cancellations and work out an expression for V3. So let's cancel out one of those factors of r like so. And what we're going to get is that V3 squared will be given by GM Now sine of 60 is just, what is it, root 3 divided by 2, so this will just cancel out this factor of 2 like that. Let me just kind of write it more clearly, multiplied by 2, where those two factors are going to cancel out. And then we have a factor of 4r cosine squared of 30 degrees. I think that's right. Okay, what was this problem actually asking us to do? What is the speed v3 in terms of v2? So we've got an expression for v2, which is gm over 4r square rooted. So we can quite easily express v3 in terms of v2, because v3 is going to be the square root of all this, gm over 4r. Notice that this here is essentially our v2 multiplied by, now what we have left up here, and this whole thing is square rooted, remember, is square root of the square root of 3, nothing else at the top, and then we just have a factor of cos squared 30. Now this is probably best to be inputted into a calculator, but this thing over here, that's just v2. So let's put the rest into a calculator. Square root of 3 over cos of 30 degrees squared. And this here is going to give me a factor of around 1.52 v2, which is our final answer. Okay, next one. Two identical spacecraft of mass m are in stable circular orbit around the Earth. One is at a height re, where re is the radius of the Earth. Okay, so let's just draw this. This is likely to be a tricky question. This here is the Earth, and it has a radius re. We're going to have one satellite, which is going to be at the same radial sort of height above it. In other words, its total height is going to be twice re above the center of the Earth. I'm just going to say that this here is, let's give it a little name. So this one here is satellite A, and then we're going to have another one which is at a height 2re. So we're going to add yet another distance. We're going to place our second satellite. I'm just going to call this satellite here. Should we just call it B? Very imaginative. What is the difference in the total energy between the two spacecrafts? Okay, well, the difference in energy, delta E, will be given by, let's say, EA take away EB. The total energy of the satellite is given by its kinetic and potential energy. So the kinetic energy of EA is just a half mVA squared. Take away, remember gravitational potential energy is always negative, so it'll be minus gm m, where this here is the mass of the Earth. Let's call it capital M. And then divide that by m, divide that by its radius, which is just going to be 2re, because that's its orbital radius. They're always taken with respect to the center. The distance from here to here is just 2re. Okay, now for the other one, we're going to take away its kinetic energy, which is going to be a half m, and then vb, it's going to be moving at a different speed that we'll be able to find out later, squared. And then take away its potential energy, but then we have a double negative, so this here is going to turn to a plus, so it will be gm, where m is the mass of the Earth, multiplied by m, and then divide that by its distance, which is just going to be 3re. Okay, cool. So we can't really do that much with this expression until we find out the speed. Actually, maybe we can tidy this expression up a little bit. So I'm just going to say that this here is equal to a half mVA squared, and then we can take a factor of gmm over re. What do we have left? We have a third. take away a half, and then we have another factor of a half mv squared, so minus a half mvb squared, like this. Okay, we can tidy this up even a little bit more. So what I'm going to do is I'm going to group the kinetic energies as well. So I'm going to go a half m, and then we can factorize this out, and what we're going to get is VA squared take away VB squared. And then if we were to tidy up the GMM fraction, we're going to get plus GMM over RE. Now 1 over 3 minus a half, this here is just going to give me a factor of minus 1 over 6. So one way to figure out the speeds in orbit is just to use the fact that they're circular orbits. So we can always in general say that for a circular orbit, the centripetal force is provided by the gravitational force. So let's just quickly rederive this expression. mv squared over r will be given by gmm over r squared. So this would mean that the orbital speed v will be given by gm, where m is the mass of the planet, divided by the radius square rooted. Okay, so we can apply this for a, and we can say that va will be given by the square root of g times the mass of the planet, and then we're dividing it by its orbital radius, which if it's orbiting at this position, this here will just be 2re. Similarly, we can say that VB will be given by the square root of GM over 3 times RE. So we can absolutely see that VA over VB, if we were to find a common factor between them, will be given by GM over 2RE multiplied by, if we're divided by a fraction, we multiply by the inverse, square root of 3RE, divide that by GM. Now, pretty much everything is going to cancel except for those factors. So we get that VA over VB is just given by the square root of 3 over 2, which means that VA is equal to root 3 over 2 multiplied by VB. Okay, now we've got an expression for how those two velocities are related. So we can say that this here will be given by a half m times VA squared is just going to give me 3 over 2 VB squared take away VB squared, like that, plus GMM over RE multiplied by that factor of -6. Okay, well, this here we're just going to give me a half m multiplies 3 halves, take away one of them, is just going to give me a half VB squared plus all the rest. And we can just rewrite this as 1 over 4m. And what do we have left? VB squared take away a 6th GMM over RE. Okay, we're almost there, guys. So what I'm going to say then is that this expression right over here, I'm going to carry on the working out here. The change of energy, or the difference in energy, will be given by 1 over 4 m. Now, what is VB? Remember, VB was just this expression, square root of GM over 3RE, which means that if we square this, we're going to get a factor of GM over 3R subscript E. Okay, take away a 6th GMM over RE. Okay, now let's take a common factor out. I'm going to go with GMM over RE. And then what do we have left? We have 1 over 4 and 1 over 3. That's going to give me 1 over 12. Take away 1 over 6. Okay, so this here is going to give me a final answer of minus G, a final, which is equal to GMM over RE. Let's just be careful with the fractions. 1 over 12 minus 2 over 12, like that, which is going to give me a factor of minus 1 over 6. GMM divided by RE. One thing though, I've introduced another variable over here, m, which is the mass of the planet. Now, because the mass of the Earth will be providing that GP, that gravitational potential energy, I am expecting it to be part of the answer. However, typically in questions, I quite like to give my answer only in terms of the variables that were given. I don't think I can do it this time. If you spot a trick that I've not spotted, can you please let me know in the comments, or if you spot a mistake in the working out. But hopefully the method of this makes sense. So we have a negative point charge with charge minus Q lies on a line between two fixed positive charges. Okay, so let's just draw this. So here is our line like that, and we are going to have Q1 on one side. We're also going to have Q2 on the other side. Okay. The negative charge minus Q is going to lie somewhere here. Assume that the charge Q1 lies at x is equal to 0. So we can say that this line here is x is equal to 0. And then the other one lies at x is equal to a. Okay. So find all positions where the charge minus Q experiences no net force from the positive charges for the case in which Q1 is equal to Q2 and Q1 is not equal to Q2. Okay, so let's say that this distance here is x, like that. And that would mean that the other distance from here to here, well, what would that be? That would just be x minus a. So in the first instance, when the charges are equal, the charge will experience a net force of 0. So the first case to consider is whenever Q1 is equal to Q2. Let's say that this here is equal to Q. The only variable here will be the distance. So as long as they are equidistant, then the force will be exactly the same. So if that's the case, what we'll need to do is place our negative charge right in the middle. So this will happen when it is placed at, so minus Q should be at a over 2. So first little case is pretty easy. Now, if they're not equal to one another though, this is where it gets a little bit more interesting. What are we going to have? We're going to have two forces. So let's say that this thing is going to be attracted this way by a force, but it'll also be attracted this way by a force as well. Let's call these F1 and F2. So F1 will be given by Q1Q over 4 pi epsilon naught x squared. F2 F2, on the other hand, will be given by QQ over 4 pi epsilon naught. The distance between the charges is just going to be x minus a squared. Okay, so we're looking for positions where F1 is going to equal to F2. So we can set the two equal to one another. Q1Q over 4 pi epsilon naught x squared will be equal to, this here should be Q subscript 2, Q2 Q over 4 pi epsilon naught x minus a squared, like that. Okay, so we can do a little bit of simplification. Let's get rid of these charges. Let's get rid of 4 pi epsilon naught. And I'm going to bring the q's onto one side. So I'm going to say q1 over q2. This here will just be equal to x squared over x minus a squared. Okay, so this is looking like it will probably turn into an interesting quadratic equation. Let's see what's the best way of actually dealing with this. I'm going to say that q1 over q2, and then we're going to multiply this by x minus a squared, and then what we have left is that this thing here will equal to x squared, so this take away x squared will just be equal to 0. Okay, so we have x minus a squared take away x squared, so we can do a little bit of simplification. So we can say that q1 over q2, let's factorize this out. What are we going to get? X squared minus 2xa plus a squared, if I remember correctly. The formula, yeah, that should be fine. And then take away x squared like that, and that is going to be equal to 0. Okay, well, we are ready to tackle the next part. So tell you what, I'm just going to rewrite this over here, and then I'm going to expand this a little bit further. So what is that going to be? q1 over q2 x squared take away q1 over q2 2ax plus q1 over q2 a squared take away x squared is equal to 0. So let's get all the terms with x squared out in front. What are we going to get? We're going to get that x squared multiplied by q1 over q2 take away 1, then minus 2a q1 over q2x, and then plus q1 over q2 a squared is equal to 0. Okay, so we have got a quadratic. Now, I'm not going to try and factorize this. I think I am just simply going to try and use the quadratic formula. So I'm just going to write it over here on the side just to make my life that little bit easier. I'm going to say that x is equal to minus b plus or minus b squared minus 4ac divided by 2a. Okay, let's apply this to our expression. We're going to get that x will be equal to the following. So what are we going to get? Our minus b is going to be plus 2a q1 over q2. Then we're going to get plus or minus a big square root. We're going to have b squared, which is going to be 4a squared q1 squared over q2 squared. Okay, minus 4ac, so it's going to be 4 q1 over q2, take away 1, that's our A, multiplied by our C, which is q1 over q2. I'm hoping this is going to turn out right, multiplied by A squared. Then what are we going to do? Divide that by 2A, so over 2. A is this one here, q1 over q2, take away 1, like that. Okay, so I can see quite a lot of factors of q1 over q2. So I can probably do a little bit of factorizing. So this here will be given by, let's take a factor of q1 over q2, and then what are we going to get? We're going to get 2A and then plus or minus the square root of. Okay, I think this here is going to work out pretty nicely. Now from here I need to take a factor of q1 over q2 squared, because then it will be square rooted. So this here will actually gonna give me 1 minus, and then this thing divided by that factor, which is just going to be q2 over q1. And then this factor here will disappear because that will be included into this. Some tricky algebra here. Then we've got a factor of a squared. Okay, hopefully the lower part is going to be a little bit less tricky. So let's take a factor of q1. So we get a factor of 2, then q1 over q2. What are we going to get? We're going to get 1. And then minus, pretty much the same as we did, q2 over q1. Okay, that here is looking pretty good so far. Let's see, is there anything else that I could take out? Yeah, I can probably actually take out a factor of 2 here. Because then this will disappear and these factors of 4 will also disappear. And then look at this, beautiful, I can just cancel these, and what I should be left with is just going to be okay. Oh wait, I've just spotted that we can also take out a factor of A as well out of this. So let's just factorize this. This will not be cancelled out, but A, 1 plus or minus the square root of, okay, let's be careful, what is going to be left? 1 minus, and then 1 minus q2 over q1, like that, divided by 1 minus q2 over q1. Okay, well, let's simplify this further, especially the top part. What is that going to be? A, 1 plus or minus, okay, square root of 1 minus 1, that's just 0, so that will be plus or minus square root of q2 over q1. Okay, nice and simple so far. And then right underneath we are going to have 1 minus q2 over q1. Actually, we should be able to do some cancellation in a minute, so we can rewrite this even further, because we can see that we can probably express this as a difference of squares. So what I'm going to say is that this here will be equal to a plus or minus a square root of q2 over q1. Okay, and then this here will be you can think of this as 1 squared, take away the square root of q2 over q1 squared, like that. Okay, well, this here will be equal to a plus or minus A square root of Q2 over Q1. Divide that by 1. Take away the square root of Q2 over Q1. I wish I'd given this a different variable, this factor of Q2 over Q1. 1 plus the square root of this guy, Q2 over Q1. Cool, now we're ready to actually work out some solutions with the plus or minus. So, shall we just say solution 1? Okay, so this here is our plus solution. So this here will be A plus A over root Q2 over Q1 divided by 1 plus root Q2 over Q1, and then 1 minus root 2 like that. Okay, that here is our solution 1. Actually, even better, let's just express the top as a 1 plus that. And look at this. This thing here is fully going to cancel out. Beautiful. So our first solution is going to be A over 1 minus root Q2 over Q1, like that. And the other solution is going to be A, so solution 2, 1 minus this factor. So in solution 2, those ones are going to cancel out, and what we're left with is going to be A over 1 plus root of Q2 over Q1. And that was quite a lot of algebra with 2 possible solutions. Okay, let's do one on the Bohr model of the atoms. So following Bohr, we assume that hydrogen-like atom may be modeled as a single electron in a circular orbit around a much more massive nucleus with a charge plus ZE. But balancing forces find the speed of the electron in terms of the orbital radius. So the way we tackle these problems in the Bohr model of the atom is by looking at the net force of the electron. So the net force has to be, if it's moving in a circle, will be the net centripetal force. So that will be mv squared divided by r. And this here will be given by the total charge on them. So the, let's say Q1 over Q2 over 4 pi epsilon naught r squared. Now our Q1 is just equal to the electron charge, well, minus that. Our Q2, we're just going to be taking the magnitude of that, will be given by, our Q2 will just be given by the proton number multiplied by the number of electrons. Okay, so we can just rearrange for the speed. And we can say that V will be the square root of E multiplied by ZE. Once again, we're just taking the magnitudes out. Let's tidy up some of those R. So this one is going to cancel, leaving us just with a factor of R here. So what have we got left underneath? We've got a factor of 4 pi epsilon naught. And then we have R, and then times M. Okay, cool. So far, so good. A is not too bad. Let's have a look at part B. So for part B, show that the total energy of the electron is equal to the negative of its kinetic energy. And we're given the expression for its potential energy is given by the following expression. Okay, well, we're going to need to work out its kinetic energy, and probably the 2 questions are going to be connected. So our total energy is going to be equal to the kinetic energy plus the potential energy. So we don't know the kinetic energy just yet. Let's see if we can just figure this out across here. So this here will just be a half mv squared. What is that going to give me? It's going to give me a half m. Now v squared is that, so this will be multiplied by ze squared. And then I'm going to be dividing that by 4 pi epsilon naught m r. Okay, I'm ready to do a little bit of cancelling out. Let's see what we're going to get. The m's can go like that. So we should get, for the kinetic energy, a half ze squared, divide that by 4 pi epsilon naught r. I think that's right. Okay, so the total energy is just going to be the kinetic energy plus the potential energy, so it will be whatever we just found, a half ze squared, divide that by 4 pi epsilon naught r, and then the potential energy is negative, so I'm gonna take away ze squared over 4 pi epsilon naught r. Okay, so this looks pretty good so far. I can just put these underneath a common denominator, because a half times a quarter, that's just an eighth, isn't it? So let's put these underneath a common denominator. So what we're going to get is ze squared take away. Here we have ze squared, so it'll be take away 2 times ze squared. And then what do we have underneath? 8 pi epsilon naught r. Okay, so this here will give me minus ze squared. I think we've got this, 8 pi epsilon naught r, which is actually, let's write this in red. This is equal to the negative of the kinetic energy. So the kinetic energy was just here, that was just ze squared. A half times 4 pi is just 8 pi epsilon naught r. Okay, so we're done with B. Let's have a look at part C next. Okay, for part C, assume that the electron, the product MVR is equal to N times H bar. Find an expression for the electron energy in terms of N, which does not depend either on V or on R. Okay, so we can find an expression for V and hence for V squared. Okay, so I can directly rearrange the expression given for V. So we can say that V is going to be equal to N H bar divided by M times R. So we can say that V squared will be essentially this thing squared. However, we already have an expression for V, don't we? Or for V squared. So I'm going to take this expression we found in part A, square root of all this stuff, and set that equal to that. This will probably bring us somewhere. So this here will be given by ze squared, divide that by 4 pi epsilon naught m r. Cool, so we've got an expression for V squared. Now there's a few different ways of tackling this. One way, because what we want to figure out is an expression for the electron energy which does not depend on the speed or the radius. What I'm going to do is I'm going to rearrange this for the radius, this entire expression here, for R. After I've rearranged this for R, I'm going to plug this into the expression that we found for the kinetic energy. So minus ze squared 8 pi epsilon naught r, and for the total energy, excuse me. And then that will give me an expression which hopefully will not depend on any of the other quantities. So that's my plan of action. So let's do a little bit of rearranging. R, well, let's take this into steps, make sure that we don't make a mistake. So this here will be given by N squared H squared over M. I'm going to write a factor of R because that will have cancelled out one of the R's on the other side. So this here will be equal to ze squared 4 pi epsilon naught M. and then this R here will have cancelled out with the square before, so I can just get rid of it like that. Okay, let's rearrange for the radius. The radius will then be given by, let's see if we can do this quickly and correctly, 4 pi epsilon naught. The m's here are going to cancel. What do we have? We have a factor of n squared, h bar squared divided by m. And then we have the factor of ze squared down here. Okay, now we're going to sub this into this expression. So the total energy, I'm going to say that energy was equal to, I'm just going to copy this down, minus ze squared over 8 pi epsilon naught r it was. So this here will then be equal to minus ze squared over 8 pi epsilon naught. Now r will be given by 4 pi epsilon naught n squared h bar squared. Then we've got the factor of m ze squared like that. Okay, let's see if we can tidy this up a little bit. Okay, so this here will be given by minus, we only have one factor of m, don't we? Okay, minus z squared e to the power of 4. Divide that by 8 times 4 is 32. We've got a factor of pi squared epsilon naught squared n squared h bar squared. I think that is right. Please let me know if you spot a little algebra mistake or something of that nature. Okay, part D. So if n is equal to 1, which is equal to minus 13.6 electron volts for hydrogen, what is n is equal to 3 for once ionized helium? So when n is equal to 1 and z is equal to 1, and that's the case for hydrogen, we're going to have minus 13.6 electron volts be equal to this expression over here. All I've done is I've taken this formula and I've said z is equal to 1 and n is equal to 1. Okay. Now, for the next case, for helium, and in particular, n is equal to 3, and then z is equal to 2. We can find an expression for the total energy, which, let's just take the factor of minus z squared over n squared. And look at this. What are we left? We're left with m e to the power of 4 over 32 pi e naught squared h bar squared. But if we look closely, we're going to see that this expression here is actually just going to be equal to 13.6. So this means that the energy will be equal to minus z, but now z is 2, so it's going to be 2 squared. Divide that by n squared, which is going to be 3 squared. Multiply that by all of this stuff, which is just 13.6. And we'll get around 6.0 up to two significant figures, minus 6.0 electron volts for the energy at n is equal to 3 for helium. Okay guys, hopefully this was useful.
Well done, you have solved lots of different problems. There is one particular technique though which is not included in this video but is definitely included in this problem, and you absolutely need to have a look at this to ensure that you get the maximum possible result.